In this video, we are going to take a look at the orthogonal projection onto a subspace. So if S is a subspace of an n-dimensional vector space V, and lowercase v here is a vector in S, then V can be written uniquely as a sum of a vector from S and a vector from the orthogonal complement of S, or what we can call S perp. So we can say any vector V, lowercase v here in vector space big V, is going to be written or can be written as a form of S1 plus S2, where S1 is in S, the subspace, and S2 is in the orthogonal complement of the subspace. And that's because we know that V is the direct sum of S and the orthogonal complement to the subspace. So then we are able to say that S in S1 in S is the orthogonal projection of V onto S. And we're going to write that proj, short for projection, subscript S, with a V here. So we read that just like we did in the earlier part of chapter 2 as the orthogonal projection of V onto S, where the subscript is the space we're projecting onto, or the vector we're projecting onto. All right, so our theorem that we want to prove is that V minus the projection of V onto S is orthogonal to every vector in S. So here's our proof. V can be written uniquely as V equals V projected onto S plus S2, where S2 equals V minus the projection V onto S. And so that's going to be in S perp, or the orthogonal complement of S. So since V minus the projection of V onto S is in that orthogonal complement, or what we call S perp, then V minus the projection of V onto S is going to be orthogonal to every vector in S. So this gives us theorem 5.15, which is the theorem about orthogonal projection and distance. So we're going to let S be a subspace of an n-dimensional vector space V, and then lowercase v is a vector in that vector space. Then for all u's in S, where u is not equal to the projection of V onto S, the norm of the distance between V minus the projection of V onto S is always going to be less than the norm of the distance V minus u, where u is any other vector. So in other words, what we're saying is the projection of V onto S is the vector in S that's closest to V. And so we've got a visual over here. So we can see here is V. And then here is V projected on the S. And so if we're trying to go from V down to any other vector in S, and S is this blue plane here, we see the distance between V and projection of V onto S. I'll circle that in yellow. This is always going to be the least distance. So our other dashed line out here to U, the distance between the V minus U, this should say V minus U here, not projection of V onto S minus U. So that distance V minus U is always going to be a further distance than the distance between V and the projection of V onto S. So visually we see it okay with our diagram here, and you could practice drawing other vectors U down in that plane that is S and try to see, oh yeah, you can't get any closer than that distance from V to the projection of V onto S. So we'll take a look at the proof. We're going to let all U in S be such that, you know, it's not the projection of V onto S. These are some other vectors. So that V minus U equals the projection, equals V minus the projection of V onto S plus the projection of V onto S minus U. So all we're doing is subtracting and adding in this projection of V onto S. So that's not going to change the equation because we're adding and subtracting the same amount. But what we are able now is to break this up into two parts. So the first part here V minus the projection of V onto S is going to be orthogonal to the projection of V onto S minus U. So by the Pythagorean theorem, we've got our right angle or our perpendicular intersection. So we can say the norm squared of V minus U equals the norm squared of V minus the projection of V onto S plus the norm squared of the projection of V onto S minus U. And so this is where we've got for sure that the projection of V onto S minus U is greater than 0 because they're different vectors. We ensured that U is not equal to the projection of V onto S. So therefore, we can say for sure, you know, the norm of V minus U squared is going to be larger than the norm of V minus a projection of V onto S squared, because this part right here, I'll circle it to see in yellow, this is non-zero. So if we take it out, of course, we're going to have that strictly greater than inequality. And then we can just root both sides and get this relationship. The norm of V minus U is greater than the norm of V minus the projection of V onto S. All right, so now to solve our least squares problem, we need AX minus B to be in the orthogonal complement of the column space of A. That is this R of A perp. And we know, well, that's just the null space of A transpose. So A transpose times AX minus B quantity equals 0. Or solving this, we can distribute the A transpose through and move the A transpose B to the other side. We're looking for solutions to A transpose AX equals A transpose B. And that's the solution to our least squares problem. So you can see over here, this is just our least squares diagram, and we're saying this distance here, the norm of AX minus B is going to be our least distance from vector B to AX, which is down in the column space of A, which is our blue plane here. So we're going to finish that first example from the beginning of the section. So here's our diagram here with the points that are not a perfect line, and here's our list of points. And so we're trying to find the line of best fit, and that's going to have the least overall errors. So we say it's got the least squares for the errors, and the errors are just the difference between where the point actually is and the line. These points are really close to the line, so I can't quite draw them on there, but you've definitely seen in science class or in statistics diagrams, those error bars showing the difference from the point to the line or curve of best fit. All right, so we're looking for the coefficients C0 and C1 to find the equation of this line, y equals C0 plus C1, that best fits these points. Okay, so we know that we've got our coefficient matrices here. The 1, 1, 1 corresponds to the coefficients for the C0s. And then the 1, 2, 3 are the t values, which are going to get multiplied by C1 because C1 is our slope. And all of this has to equal our y values here, the 0, 1, 2, 3. So that's t and y here. So we're going to let matrix A, of course, be our coefficient matrix. The 1, 1, 1, 1, 2, 3 is columns. And then matrix B is going to be our y value, our solutions. And matrix X is going to be those coefficients we're looking for, C0 and C1. All right, so we've got A transpose AX equals A transpose B. And so this is our matrix here. So A transpose A, when we work that out, we get a 2 by 2 matrix, because that's going to be A transpose 1, 1, 1, 2, 1, 3. multiplied by 1, 1, 1, 1, 2, 3. So we're multiplying a 2 by 3 matrix and a 3 by 2 matrix. So we end up with this 2 by 2 matrix. So this is where the 3, 6, 6, 14 came from. You can verify. And then now we've got to find A transpose B. So that's where the 411 comes from. So A transpose B came from this calculation. 1, 1, 1, 2, 1, 3. And then B was 0, 1, 3. So that is the 411. Okay, so now we've got our values here. So now to solve for C naught and C1, we just do A transpose A inverse here. So that's this 3, 6, 6, 14 by A transpose B. And so we got our coefficients here, negative 5/3 and 3/2. So you can see that's how we get our equation. So we've got y equals 3/2 t minus 5/3. And this is that line that we see drawn through here. That's the best fit line for the points. Back in section 1.3, you were finding polynomials to fit points. So in those calculations with the matrices, you were finding polynomials that pass through all the points. So now we're going to take a look at a polynomial of best fit. So here's our data table, and here's a graph of our points, and we can see we can fit a quadratic through these points as a best fit, but it's not going to be an exact fit. So we can't use the techniques from chapter 1.3. We have to use our least squares techniques. So a quadratic is going to have coefficients C0, C1, and C2. And it's going to be the form y equals C0 plus C1t plus C2t squared. So we put our equations here into form with C0, C1, and C2. Plugging in our t values. So that first row, t is 0, and we're putting that equal to 2. The second row, t is 1, and we're putting it equal to our y value of 1.5. The third row, t is 2, and we're putting it equal to our y value of 2.5. And then the third row, t is 3, and we're putting that equal to our y value of 4. So we can come up with this coefficient matrix A here, multiplied by our coefficients C0, C1, and C2, and then this all equals our y values. So we'll call our y values B. So we've got our B matrix here. And so now we just go through the calculations, A transpose A and A transpose B. And so X is going to equal A transpose A inverse, because we're following the same steps as this previous example, where over here, once we found A transpose A, then we inverted it to isolate the coefficients. And then that gets multiplied by A transpose B. And so you can verify the calculations in SIMPy or another matrix calculator. You're going to get our coefficients here. C0 is 1.95, C1 is negative 0.8, and C2 is 0.5. So this formula right here, we use very often in statistics. So if you take a calculus-based statistics class, you will use this formula to find these coefficients for curves of best fit or lines of best fit if you are working with just C0 and C1 as your coefficients. So when we put these together, here's our polynomial of best fit. Y equals 1.95 minus 0.8t plus 0.5t squared. And you could do this working with, if you wanted to verify it, you could work with Excel to do a curve of best fit, or you could do polynomial regression in a graphing calculator, or Wolfram Alpha, or GeoGebra. I believe all of those will find these polynomials or lines of best fit using regression analysis. Earlier, when we were doing calculations like this, we were also able to check them in regression in all of those software options, because if your points are perfect matches for the curve, of course, a regression analysis is going to give you the same equation as you'll get when you're finding the perfect match that goes through all the points. But regression also works when we've got just the closest fit, not an exact fit. Okay, in the next section, we are going to do some more applications with inner product spaces. So you can watch those videos next.